Hello everyone, welcome to this applied remote sensing training on monitoring water quality of inland lakes using remote sensing. Today part 1 is going to be about overview of remote sensing observations to assess water quality. My name is Amita Mehta and I will be conducting today's session with the help of my colleague McCartney. We'll start with a brief introduction to ARSET, or Applied Remote Sensing Training Program, which is a part of NASA's capacity building program. ARSET provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, and tools. And trainings include a variety of applications of satellite data and are tailored to audiences with a variety of experiences. ARSET's thematic area for training are listed here: agriculture, climate and resilience, disasters, ecological conservation, health and air quality, and water resources. ARSET trainings are online or often they are in person. They are live and instructor-led or asynchronous and self-paced through ARSET website. All trainings are cost-free. They are multilingual or bilingual for sure. Most of our trainings have material available in Spanish, and many of our trainings are conducted in Spanish. We only use open source software and data and accommodate differing levels of expertise. So we'll start with an overview about monitoring water quality of inland lakes using remote sensing. Overall training objectives are given here. By the end of this training, you will be able to identify remote sensing observations useful for assessing water quality parameters in inland lakes, recognize the importance of in situ measurements together with satellite observations in developing methodologies for operational water quality monitoring, obtain an overview of cyanobacteria assessment network or CYAN, an early warning system to assess algal blooms in freshwater lakes, and access satellite data and develop methodologies to assess water quality parameters. Here are some prerequisites, including fundamentals of remote sensing. We recommend that you look at monitoring coastal and estuary and water quality using remote sensing. This is the latest water quality webinar that ARSET did and has a lot of useful information which will help you follow material in this training also. So there are 3 parts to this training. Today we will be talking about overview of remote sensing observations to assess water quality. Here's a note about homework. There will be one homework will be open on July 25th through ARSET website, and it will be due on August 10th of this year. And a certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. So water quality of freshwater lakes, streams and reservoirs, so all freshwater inland bodies, it's useful to monitor water quality because they impact human health through bacteria and pathogens in the water. They make water unsafe and for drinking and for recreation. Similarly, aquatic life and ecosystems are affected by water quality in freshwater bodies, such as chemicals in surface water can harm ecosystems and aquatic plants and animals. In the US, Environmental Protection Agency or EPA develops statewide water quality criteria based on the Clean Water Act, which is periodically revised. There are several factors affecting water quality of freshwater systems. They are both of natural and anthropogenic origin. They influence freshwater quality in lakes and reservoirs, in streams and rivers as well. These include pollutants from stormwater, excess nutrients from runoff from agricultural areas and wastewater discharges, water temperature changes associated with the change of land cover around water bodies. Also, climate change affects water temperature, and changes in water flow. All these factors can influence water quality of lakes. There's one example here for Lake Tahoe, and what this shows is annual average Secchi depth. So that's an indicator of water quality. Deeper you can see in the water, clearer the water is. So you can see that starting from 1965 all the way to 2020, there is a trend that water clarity is decreasing. Seki depth is decreasing here. So typical in situ observations of water quality in freshwater systems are listed here. They include chlorophyll concentration, temperature, water clarity, nutrients, metals, pH and alkalinity, dissolved organic matter, phytoplankton species, cyanobacteria, condition of indicator species such as fish or other animals and aquatic plants, suspended sediments, E. coli, bacteria, and plastics. All these are collected from water sample and analyzed to diagnose water quality in freshwater lakes. In the US, water quality monitoring data are available from the US Geological Survey or USGS, EPA, and the US Department of Agriculture, distributed through this NASA water quality portal. And the link is provided here. Multiple years of data for multiple lakes and streams are available through this site. These measurements are point measurements, and they do not provide complete spatial coverage of water bodies or lakes. Water sample collections and analysis of water quality monitoring can be expensive and may not have uniform temporal coverage. The measurements are really infrequent, as you will, if you go to this website and go through the data and search, you will see that they're not always uniformly distributed in time or space. And that brings us to the reason why we use satellite remote sensing for monitoring water quality. So satellite data, they provide regular and consistent observations over a large area. And you can see that in the example shown here. This is western part of Lake Erie, and the buoy data collected by NOAA, they are shown here as dots. You can see that these are point measurements and they don't cover entire lake. Whereas here you can see image from Landsat satellite. The green area here shows algal bloom, and you can see that the coverage is there, and then you can see this continuous distribution of cyanobacteria or algae in the western part of lake, which would be hard to see from point measurements. So their consistent revisit rate for well-structured time series analysis, because satellites have regular revisit period. Large number of data products are available from satellite. They complement in situ sampling. As we will see, just satellite data are not enough. We do need in situ data. And mostly we are going to talk about free and open access satellite data. So they're quite useful for water quality monitoring in lakes. So here are some water quality indicators that satellites can observe. Color dissolved organic matter or CDOM, chlorophyll A or phytoplankton concentration, total suspended solids, fluorescence line height, that is relative radiance leaving water surface, euphotic depth, that is the depth until which light can penetrate and vegetation can grow, diffuse attenuation of light, that is at a particular wavelength how light is attenuated in water column, that is diffuse attenuation, and it's in terms of coefficient at a particular wavelength. Sea surface temperature and salinity, so these are measured by satellites. Here is an example or an image of satellite retrieval of water clarity again. This is for Lake Winnebago, and you can see that water clarity near the coastal region is poor. As you go to this blue-green interior part, water quality is a little better. So that brings us to today's session, part 1. It's overview of remote sensing observations to assess water quality. Overall objectives for today's sessions are: will describe state-of-the-art high spatial and spectral resolution observations for water quality remote sensing and their access using Google Earth Engine or GEE. We'll understand algorithm development procedure for remote sensing of water quality, describe selected open source in situ measurements of water quality parameters, and then we will have a demonstration and exercise. So overall objective for the entire training is that we use satellite data and in situ data to develop algorithm, or at least learn the procedure to develop an algorithm for water quality monitoring. So as a preparation, today we will do these steps. We will first of all introduce Google Earth Engine. Then we will explore and download in situ measurements of water quality parameters. We will focus on chlorophyll A concentration, total suspended solids, and water clarity in terms of Secchi depth. We'll take a case study in Lake Erie. Then we will also access optical reflectance data from various satellites for Lake Erie using GEE. So that's going to be a demonstration, and then there will be in-class exercise. You will have some time to explore GEE. We will provide you scripts that you will be able to use and repeat some of the steps that we show here to get in situ and satellite data for area of your interest. Outline for this part is we'll have satellite observations for water quality monitoring, remote sensing of water quality parameters, what is involved in that, then overview of selected in situ water quality data, and then we'll have the demonstration case study of Lake Erie that I mentioned. We'll download in situ data for Lake Erie from this particular data set, the Global Reflectance Community data set for imaging and optical sensing of aquatic environment, or GLORIA. Then we will learn to access Landsat 8, Sentinel-2 and Sentinel-3 optical reflectance for Lake Erie using GEE. Just a note about how to ask questions. So please put your questions in the questions box and we will address them at the end of the webinar. Feel free to enter your questions as we go. We will try to get to all the questions during the question and answer session after the webinar. The remainder of the questions will be answered in the Q&A document, which will be posted to the training website about a week after the training. We'll start with satellite observations of water quality monitoring. Okay. So here's the current satellites and sensors list for water quality monitoring. So satellites, sensors, and this is special resolution provided here for each satellite. So the current Landsat satellites flying are Landsat 8 and 9. As you may know, Landsat is a long flying mission. It started in 1972, but the current satellites are Landsat 8 and 9. Has a sensor, it's operational land imager, or OLI, and OLI2 or 9, Landsat 9. Swath width for Landsat is 185 kilometers. And the pixel resolution is 15 meters, 30 meters, and 60 meters depending on the band. And the revisit time for Landsat is 16 days. So any place, every 16-day satellite goes over that place and takes observations. Terra and Aqua, these two satellites have MODIS, or moderate resolution imaging spectral radiometer. As you can see, the swath width is much higher than Landsat here, 2330 kilometers, but the pixel resolution is moderate. It is not as high as Landsat. It's 250 meters, 500 meters, and 1 kilometer, depending on which band you're looking at. But the revisit time here is 1 to 2 days. These are NOAA satellites, SNPP and JPSS. Has visible infrared imaging radiometer suite, or VIRS. This is similar to MODIS, has broad swath width about 3040 kilometers, and pixel resolution is again in moderate range, 375 meters to 750 meters, and 1 to 2 day revisit time. Sentinel-2A, 2B, and Sentinel-3A and 3B. These are European Space Agency satellites with data are available, they're open source. And the sensors are multispectral imager or MSI on Sentinel-2. It has slightly wider swath than Landsat here, 290 kilometers. And resolution is pretty high, 10 meters, 20 meters, and 60 meters, again depending on bands. And temporal revisit time is also high, it's 5 days. Sentinel-3A and B has multiple sensors. One of them is Ocean and Land Color Instrument, or OLCI. The swath width here is 1270 kilometers and moderate resolution pixel size of about 300 meter and 27-day revisit time. So as you can see, all these satellites have varying spatial resolution and temporal revisit time. And so depending on the where the lake you're looking at or water body you're looking at, you can pick whatever satellite sensors are available to look at water quality. Here is, you see the swath width or images for all the satellites that we talked about. And here it shows narrow swath for Landsat, slightly wider for Sentinel-2, much broader for Aqua Modis, Veers, and OLCI, which is this one here. So as you can see, the swath width and resolutions are different. All these satellites that we're talking about, they are polar orbiting satellites, go from pole to pole, has ascending and descending orbits with specific time of day of observations. And they have different revisit times, as we saw. Multi-satellite data are also used for water quality information, and the references are provided here for your information. Multiple satellites and sensors, they're fused together to get water quality parameters. Here's this temporal coverage of each of the satellites we talked about. So Landsat 8 and 9, they provide coverage between February 2013 to present. Terra and Aqua from 2000 to 1999 to present. SNPP and JPSS, these NOAA operational satellites from November 2011 to present combined. Sentinel-2A and 2B are shown here. It started in June, late June 2015. Next one was launched in 2017, March to present. And Sentinel-3A and B, February 2016 to present. This one is 25th April 2018 to present. So again, temporal coverage is different. The longest time series you can obtain are from Landsat and from Terra and Aqua. Then it is GPSS and SNPP Veers, and then Sentinel time series can be put together. This table shows spectral band wavelength and bandwidth in nanometers for each of the sensors we talked about. As you can see, number of bands vary from different sensors. Bandwidths are given here in parentheses. They are also medium spectral resolution bands. All the sensors for water quality monitoring, they have optical data ranging from blue, green, red, infrared wavelengths. Landsat, only here you can see thermal infrared data available also. MODIS and Veers also have thermal infrared bands. One thing to notice here is that Sentinel-3 OLCI has a relatively higher spectral resolution compared to other sensors, and it's been widely used for water quality monitoring. Both Sentinel-2 MSI and OLCI, they have red edge bands, which are particularly useful for looking at chlorophyll concentration. Now we will have a brief review of remote sensing of water quality parameters. So what is involved in that? So water quality affects water optical properties or water color. And so looking at different wavelengths, different colors, one can infer to water quality. So natural water contains material that is optically active. Monitoring light reflectance from the water surface with remote sensing can indicate the quality of water. So here you can see depth, and this is the light penetration in open ocean, light penetration in coastal waters, how deep it penetrates in meters, and that depends on optical property of the water. So what's involved there is, here is water, there is atmosphere, this is sunlight. So solar radiation goes through the atmosphere, there is scattering of sunlight, and there is absorption also in the atmosphere. Once it reaches the surface, some of it penetrates inside depending on the water property, and so there is also upward scattering. If the water is shallow, there is also reflection from the surface below, and so the radiation then emerging here, so direct reflection and water coming from here, emitted from here, it all goes back to remote sensor. So what satellite sees is a combination of everything that goes on into atmosphere and also in the water. So some satellite sensors measure top of atmosphere or TOA radiances. The TOA radiances result from a combination of surface and atmospheric conditions, including the effects of clouds and aerosol particles. Water living reflectance depends on backscattering and absorption of radiation due to water, sediments, phytoplankton, and colored dissolved organic matters. And here you can see the wavelengths from blue all the way to near infrared region. And this is in radians. This is total top of atmosphere radiance. Here you can see atmospheric path, then this is water leaving, and this is surface reflected. So as you can see at TOA, atmosphere has the biggest contribution, and then this is the surface reflectance and water leaving reflectances. So one thing to notice is that to look at the surface, this atmosphere contribution has to be removed. Inherent optical properties of water decides color of the water. So, and that color depends on absorption by phytoplankton, non-algal particles, color dissolved organic matter CDOM, and water molecules also. Also depends on scattering of radiation in forward and backward direction, as we saw here. So here you can see the wavelengths, and this is water leaving reflectances, and you can see that different water quality parameters have different signature in surface leaving, water leaving reflectances. So for water, it's blue, it peaks in blue, chlorophyll in green, CDOM also in blue-green, and sediments more or less in red and near infrared. So looking at different spectral bands and looking at where the maximum reflectance is in water leaving reflectance, one can decide what kind of water quality there is. So again, as we mentioned earlier, it's visible to near infrared range is used for water quality remote sensing. Water quality parameters from remote sensing observations. So algorithm development has several steps. We start with top of atmosphere reflectance from satellite over a water body, and also get in situ observations of water quality parameters when there is satellite overpass. So there is co-located data where satellite is looking down and in situ data or water sample is also collected then. So this is past time series of observations, they're collected. Then top of atmosphere reflectance are corrected for atmospheric impact on TOA, and that gives water living reflectance after atmospheric correction. So using water living reflectance and in situ data, then statistical or empirical algorithm is developed for a particular water quality parameter. And that gives model coefficients based on this algorithm. These coefficients then can be applied to atmospherically corrected real-time or current satellite overpass reflectance data that provides water quality parameter. So this, and then this is past data for developing algorithm here, and then it's validated and then used with near real-time data for water quality monitoring. So that's the overall methodology. Requirements for algorithm development are: pick a geographical region or a water body where you want to develop the algorithm. In situ water quality parameter measurements, both spatial and temporal co-location with satellite overpass are required. Spectral water reflectance from satellite images, the cloud-free scenes are necessary. Seasonal to annual coverage of in situ and satellite data are preferable because there is seasonality to change in atmospheric conditions and also water conditions. Analysis and statistical algorithm coefficient derivation from the in situ and remote sensing observations then, and then independent in situ data for algorithm validation. So this is the standard requirement for algorithm development. So with that background, what we're going to do now is look at description of selected in situ water quality data that we may use for developing algorithm for inland water body water quality parameters. One such site is CWIF's Biooptical Archive and Storage System, or CBAS, that is a NASA system, and it's put together by NASA Ocean Biology Processing Group, and that maintains a repository of in situ oceanographic data to support satellite data validation. CBAS data include measurements of inherent optical properties, phytoplankton pigment concentration, water temperature, salinity, and stimulated fluorescence. Data are collected by using a variety of platforms including ships and moorings. Different instrument packages include profilers, buoys, and handheld instruments. Primarily, CBAS data are collected in coastal and open oceans. So in situ measurements data from CBAS can be downloaded and selected for some lakes. This is the website where you can get data. Go to the website. There's a get data and contribute data links here. These are some of the lakes, not many, they are included in CBAS database. And CBAS data have a specific format that information can be found on this website as well. And our earlier webinar about estuary water quality parameter retrieval has details about CBAS. USGS has a national water dashboard, and the link is provided here. It provides water quality measurements taken into streams in general, not in lakes, but several of these streams open into lakes and provide some indication of how water quality in lake may change because of that. If you go to this site and pick water quality parameters, you will see a list available for these sites. Water temperature, conductance, pH, dissolved oxygen, turbidity, nutrients, chlorophyll, fluorescence, organic and inorganic material, suspended sediments, but not all of these parameters are available everywhere. For example, here is something about turbidity. So if you pick turbidity, these are the locations where turbidity is available from water samples. By clicking on any site, you can get turbidity data or water quality parameter data that you pick. And by clicking on that site, you can also get time series of that water quality parameter, and you can find information for that site. Data can be downloaded as well by going here. Next, we have USGS lake water quality measurements from Explore Search, Lake Water Quality. These are not operational sites. The USGS works with partners to monitor, assess, and conduct targeted research and deliver information on a wide range of water resources and conditions, including stream flow, groundwater, water quality, and water use and availability. And you can select by state whenever data are collected in any lakes, they are made available. This example is for Lake Pontchartrain from Explore Search site. The data in this case are available between 2008 and 2020, and they can be downloaded as text files and analyzed. There is National Harmonized Chlorophyll Dataset. So chlorophyll data and site information can be downloaded from this site. Data are available between 2005 to 2022 whenever measurements are available. And if you go to this site, you can download data sets and data files wherever they are available. Again, all these data sets are for the US only. So here's National Harmonized Chlorophyll Dataset example. These are the measurement locations. This is the zoomed in version of these data. So you can see that measurements are available, chlorophyll measurements are available in lakes here. Center for Disease Control, they have water quality information for oceans, lakes, and river by state. So several states and local entities in the US routinely or periodically collect lake water samples and analyze water quality for health safety, focusing on harmful algal bloom. And so this site, this California shown here, and here this is Illinois, so you can see where the data are available. But they are mostly for harmful algal bloom. And then global freshwater quality data. So we talked about all the US lake water quality data, in situ data. This one site from United Nations Environmental Program that established Global Environmental Monitoring System for Freshwater, or GEMS, in 1978. Data are shared from many countries around the world and are made available via this GEM State data portal. This is the monitoring GEM State portal. It's available here, link. And when you go to the site, you can see several countries and several locations contributing to this site. But the coverage is non-uniform, and not all water quality parameters are available. For example, this is Lake Victoria in Tanzania. Here you do see a time series of total suspended solids, but that's the only parameter available. If you go to here, Iguazu reservoir, you only have one point, and it's mostly nutrients they are provided. So global data are there, but they're not uniform in time and space, and they're limited in water quality parameters. So there is one more global data set that we want to talk about, and that's the Global Reflectance Community data set for imaging and optical sensing of aquatic environment, or GLORIA. We're focusing on this data set because it is global and it is more systematic than the GEMSTAT site. So Gloria is a hyperspectral reflectance data set collected from 450 water bodies around the world. So there is actually hyperspectral reflectances are collected at the water surface, but at the same time, along with this data, at least one co-located water quality measurement is done. So sample is taken and analyzed for chlorophyll A concentration, total suspended solids, absorption of dissolved substances, Secchi depth, and these are provided along with this reflectance data. We are interested more into this water sample data. So these data are contributed by researchers from 59 institutions around the world. Data collection started in 1990, and the sampling efforts they have been steady since 2001. Here's the reference provided for this data set, and a lot of detail can be found from this document. In situ water sample from Gloria, so you can see where the data are available. Water samples were analyzed and chlorophyll A, TSS, and CDOM coefficient were determined by using well-established high-accuracy laboratory methods. Secchi depth was determined by an observer by lowering a black and white disk of 20 to 30 centimeter diameter into water body. The depth when the disk was no longer visible was noted as the Secchi depth, which reflects water clarity. The data collection, as shown here, started in 1990 but became more established after 2002, as you can see here. Some seabass inland water quality data are also included in Gloria, and there is analysis of samples are shown here. So while limited to 450 water bodies around the world, these data are open source, well organized, and distributed with detailed information. So in this training, we will use these in situ water sample analysis data along with satellite remote sensing data to learn how to develop algorithm to monitor water quality. The data are available as CSV file and they can be downloaded from this link. We will demonstrate this later today. So what we're going to do now is look at a case study. First, we'll acquire in situ data and then satellite data for Lake Erie. We'll focus on Lake Erie. We talked about this algorithm development flowchart. So here we are going to get in situ data from Gloria for Lake Erie, and then we will get Landsat 8 and Sentinel-2 reflectance data using Google Earth Engine. So before we do that, here is introduction to Google Earth Engine. For those of you who are new to this, it's a cloud-based raster computing and for remote sensing analysis it's very useful. So it's a catalog of publicly available data sets. It removes barriers and limitations related to data hosting and storage. GEE is free for scientists, researchers, and developers. This is the layout if you go to Google Earth Engine developer site. There are several tutorials and examples available on this site as well. Google Earth Engine takes advantage of cloud computing capabilities to provide users with a single place for accessing satellite data, applying remote sensing methodologies, and displaying analysis results, as shown here. GEE's Application Programming Interface, or API, allows users to easily use algorithms for various applications, such as water quality monitoring, land cover classification, weather and climate analysis. There is Application Interface, Programming Interface, or API, that Earth Engine uses, and that is JavaScript API. That is currently the most widely used method working with GEE. A Python API through Google collaboratory is also available for those interested in using that. It's a little more involved, so JavaScript is more widely used. And here is an example. Um, Uses of GEE for satellite imagery analysis include automation of data processing and display, near real-time monitoring, limited by availability of data in the catalog. Not all satellite data are available in near real time, but many are. Machine learning algorithm applications available, and graphical user interface implementation is there. So Google Earth Engine requires sign up with them. So make sure that you sign up for a Google Earth Engine account as soon as possible. If you don't have one, use this link to register. It takes a couple of days to get approval and get the account set up. A Gmail address is not required, but it is recommended that you use your work or institutional email. So here's the information about signing up to Google Earth Engine. So with that, we will start our demonstration. First, we'll look at Gloria data, how to access that. Here's the data description and here's the data access link. And for that, we want to acknowledge Dr. Nima Pehilwan. He's from NASA Ocean Biology and Biogeochemistry Group at Goddard. And he works with Remote Sensing of Water Quality Group. He co-led the Gloria program and shared this information and data with us. So let's go to this link to download the data. I have opened that in the browser, and as you can see, this is the citation. A number of people have contributed to this project. When you want to use this data, you will use this citation. So information, there's abstract, there are some keywords, and then there are comments to learn about this project. When you go down here and click here, you can download the data. Once you click here, you will get a zip file. And when you unzip this file, you will get several CSV files with the data. So let's look at some of the data sets that I've already downloaded. So the one file you will get is water living reflectances, and this is really the heart of this data set, that you have water living reflectances in hyperspectral domain. Here you can see these are the IDs, and there's information, we'll see where they come from. Although what we are going to use is there are co-located in situ data, which is what we are trying to use. And so although this is the main part of this data set, the strength of this data set is that RRs are co-located with water sample data, and they are analyzed, and you have water quality parameters, so you can develop algorithms. So this is that file. This is the data file of water samples and water parameters, Gloria Mehta and lab, and all these columns are described in this Gloria variables and methods. So you can see what the headers mean, chlorophyll A and the units, TSS and units. So you can go through this file and see what each header means in this meta and lab file. So if you go down here, there's more information, and there's also you can see that there's water type. If it is 1, it is sediment dominated. If it is 3, it is CDOM dominated. So this information is also provided. You can look at the water body type. And of course, there is geographical and time information. So this is the key to understand what all these headers mean. So I have subsetted this file. So if you look at here, this is site name. Several lakes from around the world are here. This is country, latitude, longitude, date. the water body type, and so all these headers you can look at, such as there is cloud fraction, there is depth of the water body, wind speed, etc. When you move to the last few columns, you will see water quality parameters measured in different lakes. So this is chlorophyll A, total suspended sediments, and Secchi depth. This is what we are looking at. Turbidity is there in some lakes. As you can see, not all the lakes have all the parameters, but they have some water quality measurements, and some lakes have all of them. So for our case study, we have picked Lake Erie, and here is the subset of that big Gloria file with a few columns for Lake Erie as shown here. So latitude, longitude, date and time, water body information, and then you have chlorophyll A, total suspended sediments, turbidity, and Secchi depth. So we are going to work with this file. We'll find satellite overpass which are close to these dates or co-located with this latitude and longitude. This file is available to you for download, and so please download so you can work with the exercise after we are done with the demonstration. So next we're going to start with our Google Earth Engine demo. We will start with the Google Earth Engine on my browser. I'll share that with you. We'll learn to access Sentinel-2 data, Landsat 8, and also Sentinel-3 Olchi reflectances. Just a note here that for the case study and for algorithm development steps, we will use Sentinel-2 data because it is 10-20 meter high resolution. But we will also see how to get Landsat 8 data from GEE because that's about 30 meter. And so both of these are ideal for looking at lakes. We will look at Sentinel-3 reflectance data, how to get those, because Olchi on Sentinel-3 has many more spectral bands as we saw earlier, and that also has been used for looking at water quality parameters in estuaries, in bigger lakes, and also in coastal regions and oceans. It is moderate resolution, but still it's a new high spectral resolution data set, so we will look at how to get that as well. So let me share my screen with you. This is the Google Earth Engine code editor window. Those of you who do not use GEE regularly, just a very brief overview. This is where the script name appears, and this is the main window where you have JavaScript steps that you can edit and modify or add a new script here. On the left hand side, all the scripts that you create and save by using the save button will show up, and then when you press or click on any of them, that's the script that shows up in the editor window. Docs here are Earth Engine functions which you can use for various operations and calculations. Assets where you can use or upload your own data to use in GEE for your use. So let's go to scripts. Here's the script. Once you edit, you can run and then get the results. Here you have console. Anything that you print here in the script, it appears here, and that's just for checking your results. If you are printing something, it appears in this console. There are several tasks that you can perform, and they are listed here. In this case, we uploaded a table, so that was a task that appears here. And we look at the inspector once we run this code. So just very briefly going through the code, you do have access to this code, so you should be able to copy it to your own account and modify it and run it. Run as is first, and then you can modify it. So on top we have geometry imports. We've defined a polygon covering western part of Lake Erie, where most of the Gloria in situ data for this lake are available. This table here was put together by Sean McCartney for 15th of July 2019 to show locations where in situ data are available, and those locations are actually plotted here on map by using map.addLayer table, and this is the color, the name of the layer. Now here this is a standard function that's available from GEE, and that is to mask clouds for Sentinel-2 images. Sentinel-2 MSI optical data are there, so when there are clouds present, you cannot see the surface. They block the surface, you only see clouds. And we don't want to use those cloudy pixels for algorithm development when we can't see the surface, so we are excluding that. So we are first masking all the pixels where clouds are present or cirrus clouds are present. And in the quality flag in the image, bits 10 and 11, they are cloud mask and cirrus mask. So wherever they are present, when clouds and cirrus clouds are present, those locations we are setting this mask to 0 to make sure that we don't use image data at those locations or those pixels. So that's just a standard function that we will be using with all our images that we work with. Through Google Earth Engine catalog, we select atmospherically corrected surface reflectance. So here you can just type Sentinel-2, and then all the data available from Sentinel-2 will appear in a list. And we've done that and selected atmospherically corrected surface reflectance images. So let's see, this is the image collection. This is the name, for standard name from GEE, S2 surface reflectance harmonized. We are selecting it by a date range. Let's see, this is 1st of July to 31st of October 2019. We are masking with this cloud mask so that all the pixels where clouds are present are set to 0. And then we are using this filter bound. So we are only looking at this region from all the global images. So we're isolating by date and space or region. This is print statement just to check how many images are there in this collection, and it shows up here. Now, once we have images, here are the dates where we have in situ data from Gloria. So 2019 and 2020, these are the dates listed where we have in situ water sample and water parameter data from Gloria. And then co-located Sentinel-2 data are found for a few dates, and we will see how we did that. So this is 15th of July, 3rd September 2019, and this is for 2020. So here, let's see some examples of Sentinel-2 images. This is for 3rd of June, where there was Gloria data were available then. What we have done is here we have chosen a window that's 1 day before in situ data and 1 day after the in situ data. So if any co-located images are there, then they are extracted from the catalog. This is 15th of July 2019, and this is 1st of September 2020. So these 3 images are picked. Now we've picked 1 day before and 1 day after window. Ideally, if you want to develop algorithm co-located data in situ and satellite, ideally they should be within a few hours. But for now, since we do not have so many in situ data samples, we are allowing 1 day window on each side. This is the visualization part, and we are plotting RGB images. Minimum and maximum values here are for surface reflectance, and you can change this max value depending on after inspecting your image. And the bands selected are band 4, band 3, and band 2. If you go back and refer to the band spectral band tables that we saw in the presentation, you will see that this is red, green, and blue wavelengths are covered in these bands. So these bands are chosen for RGB or true color image, although these are surface reflectances, so not it's not top of the atmosphere reflectances, but it's still RGB image. And map center we picked in Lake Erie. These map.add layer for here all three, so this is 3rd June, 15th July, 21st September, they plotted. Mean here means if there are overlapping pixels or overlapping images, then the mean value is considered here. So let's run this. Okay, when you run the script, it shows all the images available here. So let's see. When you click on the layers, all the layers are shown here. Let's turn these layers off, and also let's turn the polygon off for a few minutes. Here, these are the locations where 15th of July there were in situ measurements. RGB1 was 3rd June 2019 image. You can see that although image touches the polygon we picked, it really is it's not co-located, or there is no overpass over this in situ data. So we're not going to pick this image. So this is just an example that you might have an image in vicinity, but it's not really co-located with in situ data. So then we're not using that for algorithm development. RGB2 has good coverage here, and so does this 21st September. So 15th July 19 and 21st September 2020, they are selected. So by visually inspecting, we have made a catalog of images where we have in situ data as well as we have satellite data. And we'll use those to develop algorithms. If you see, let's see, go here where all the images were first picked, and this is the print statement. So if you look at this image collection, it says how many elements are there, and this is between June and October. And you can actually look at what is in this image collection. All the features are listed here, so different images in this collection. And for each one, you can look at the property or properties, and here is the date for which a particular feature is. And so all the images, you can look at dates and how many bands are there, etc. Last thing is the inspector. If I click, when I click on inspector and click on any of one point, it says latitude, longitude, and this is RGB1, that's 3rd June. Everything is masked. We know that there were no data here. The image was here. But if you look at RGB2 and RGB3, it tells you which band has what reflectance at that point. So you can view values. So these are surface reflectance for July 15th, 2019, and this is 21st September 2020. So let's now look at Landsat 8 data. You will be working with this script in your exercise time. Just to show you how to get the Landsat data, here's the script we have that you can use. So this is for tier 1 L2 data, that also is atmospherically corrected surface reflectance data for the same polygon we have picked for Lake Erie. And you can see this is the name of Landsat dataset in the catalog. This is collection 2 tier 1 L2. For Landsat 8 reflectance, to get into proper unit, you have to apply a scale factor, and this is provided along with the script when you go to the GEE Landsat standard script. Once you find those scale factors, then you apply the scale factor. In addition, we have applied the spatial filter to look at this area alone. And so this is pretty much following what we did for Sentinel-2. This function also is similar to Sentinel-2, where you're masking clouds. So here you have in the quality flag, bits 3 and 2 are cloud and cirrus masks. So they are set to 0 so that we can exclude those images when we try and develop algorithm. So that's exactly what we did for Sentinel-2. Here you are finding this new image collection by applying cloud mask. This is the visualization part again. Band 4, 3, 2 are red, green, and blue, so RGB images are shown here. And these are plotted here, so let's run this. Now you can see images. One just example here is that if you turn on RGB2, which is cloud-free image, and this is the original image now, you can see all the clouds here. Once you turn the other image on where it's cloud-free, so masked, you can see that most of these cloudy pixels are now masked. So this is something that you can work with or exercise, practice with once you go through Sentinel-2 script. This is just for your information. Landsat 8 also can see very many lakes around the world. So you can try using both Sentinel-2 and Landsat 8 for inland lakes. Here is some information about Sentinel-3 OLCI data that we talked about. In Google Earth Engine, atmospherically corrected surface reflectance data from OLCI are not available, which can be directly used for algorithm development. What we have is top of atmosphere radiances. So this is the catalog name for Sentinel-3 OLCI. Radiances are actual units of energy that are measured by any sensor, so in this case OLCI. If you want to convert that to reflectance, then you have to take that top of atmosphere radiance and divide by how much solar radiation is coming in with respect to that fraction of radiation is reflected back at that zenith angle. So that is involved, and then on top of that, atmospheric correction also has to be done. So from GEE, all you can get is radiance from OLG, but we can always look at the images, how it looks like. There is also a scale factor for OLG data. This is just visualization, just like we did for Sentinel-2 and Landsat. And I've already run this script, so I'm just going to show the layer for this narrow range that we picked. And let's focus on Lake Erie region again. One thing to notice here is that you do see these clouds when they're present, top of atmosphere radiance we are looking at. Also see that the swath here are much wider, order of magnitude wider than Sentinel-2 and Landsat 8. So this is a quick way to look at OLG Sentinel-3 data. If you want water-living reflectances from OLG, then this is the site, Sentinel Online from Copernicus, and there you can get water-living reflectances for 16 bands which are used for water quality measurements or estimation. And for data access, water living reflectance, you can go to access to Sentinel data, and that will take you to this Science Open Hub. So this is Science Hub for Sentinel data, and from here you can follow the instructions to get Sentinel-3 OLG water living reflectances for further analysis. So this is mainly for your information. As I mentioned earlier, we are going to use Sentinel-2 data here for demonstration. So this concludes our GEE demonstration, and I want to summarize what all we talked about today. So in summary, we described state-of-the-art high spatial and spectral resolution observations from Landsat 8, Sentinel-2, and Sentinel-3 for water quality remote sensing. We described selected open-source in-situ measurements of water quality parameters, including those from USGS Water Dashboard and Lake Water Quality Portal, National Harmonized Chlorophyll Data, UNEP GEMSTAT, and GLORIA in-situ data. We explored and downloaded GLORIA in-situ measurements of chlorophyll A concentration, total suspended sediments, and Secchi depth for Lake Erie. We searched and identified optical reflectance data from Landsat 8 and Sentinel-2 co-located with GLORIA in-situ measurements for Lake Erie, and we used GEE for that. So next session will focus on getting familiar with Cyanobacteria Assessment Network, or CYAN, and CYAN web application for monitoring toxic cyanobacteria in lakes. As a reminder about homework and certificates, there will be one homework assignment that opens on July 25th and will be available from ARSET website. Answers must be submitted via Google Forms, and the homework will be due on August 8th. There will be hands-on exercises in all sessions, including today, and you will be instructed to submit results of these exercises to our Google Drive folder. Those of you who attend all 3 live webinars and complete the homework assignment by the deadline will receive a certificate of completion via email approximately 2 months after the course is completed. Hello everyone. Let's start with question and answer. We've received several questions. We'll try and address them here, and if we cannot cover all of them, we will try and answer those and share them with you on the training website. So if you have any question or difficulty with the code or in situ data, please let us know. We'll start with the questions. The first one is, will salinity assessment be covered in one of the other sessions? Unfortunately, not in this webinar series. We will not be considering salinity. Just to make it clear, this is mostly to look at when water quality parameters, when they affect water color, that's the satellites can see that clearly, and so those are the parameters we are focusing on in this webinars. Second question is, why do I sometimes see Sentinel-2 has a revisit time of 2 to 3 days? So 5-day is for all places, at least 5-day revisit time is there, but there are 2 satellites, Sentinel-2A and 2B, and depending on which latitude you are, you can have more than that, so 2 to 3 days is possible. Question 3 and 4 are related, and that's about, does an OLCI have a 1 to 2 day revisit time? The second one says that Sentinel-3 OLCI revisit time with both satellites is just 1 day for Europe. So is it same for the rest of the world? So if you look at this Copernicus site describing revisit time and how different instruments on Sentinel-3, they have data, you would be able to see that exact scenes are repeated every 27 days, but these are wide swath instruments, and there are, over Europe, there are also sub-cycles, so you can have more frequent measurements. So you have 1 to 2 days, yes. What is TOA radiance? So TOA is top of atmosphere radiance data. That's what satellite sensors actually measure. So that is a contribution from surface and atmosphere. So when sunlight strikes on the Earth atmosphere system, there are several processes through the atmosphere. It goes to the surface, there are processes at the surface, and then everything comes back. So along the way, there's absorption and scattering going on. So what you see at the top is a combination of everything that is there in atmosphere and water column where light can penetrate. So TOA is an integrated radiance for that. Question 6. Would we be able to differentiate between floating and open water using the satellite data? No, I think from optical data, it would be difficult. There have been attempts to combine optical and synthetic aperture radar data, and we would try and find references for that or more information about that, and put it in, provide that information to you. Question 7. Why is water leaving reflectance defined differently from regular definition of reflectance? What is the need for such a definition? So for water quality estimation, we saw in the presentation that atmosphere has such a, if you look at just regular reflectance at the top, atmosphere has such a big contribution that you cannot really see water clearly, or it's a signal to noise would be low. So we remove that atmospheric part, and then what you see is just the reflectance that's coming from the water surface. So that's why we're defining water leaving surface reflectance. Question 8. What is the purpose of algorithm development and what does it mean? So algorithm development is that we saw that in situ data measurements are really not continuous. These are point measurements. So what we're doing is using these measurements co-located with satellite data and derive a relationship between water quality parameter that we observe in situ and the satellite data, how they are related, and find coefficients. So then these coefficients can be applied at all the satellite pixels to get estimation of water quality parameter. And so you can have a continuous coverage for that water quality parameter. And you can, if you derive this using a specific time series, you can then use those coefficients in near real time and current satellite data. So then even if you don't have in situ data, you can use that relationship to estimate water quality parameter. Question 9, can the basic code in GEE or any other language for retrieving water leaving reflectance be shared? Basic code to derive water quality reflectance from TOA, I'm not aware of that in GEE, but there is NASA CDAS OCSSW software that does that. You can start with top of atmosphere radiances and it derives water leaving reflectance for you. So that code is there. And this is the website. In our earlier webinars, we have used CDAS OCSSW. At that time, the older version of CDAS worked only on Linux and Mac and not on Windows. But now I believe that the newer version it can work on Windows machines as well. So in future, we will again revisit some of our older water quality issues using CDAS. Using GEE here, where you already have atmospherically corrected radiances or reflectances, was that we don't have to install and work with CDAS, and you can quickly just learn to develop algorithm. Is this data open access over the world or only for US applications? No, the satellite data that we talked about, they are global, they are open source, you can access them from GEE, they're global. And we hope that you use the code to explore other lakes in other parts of the world. Gloria data are global, but they are only for limited lakes. Okay, question 11. To monitor sedimentation deposits in a dam, we use multi-date images, sorry. How do we measure the height of these deposits with satellite images? That is a good question, and I do not have a precise answer or methodology for that, so we will get back to you on that one. Question 12 is, can we monitor water quality for lakes of really small sizes, say 80 to 100 acres, using satellite data? My experience with Landsat has been that resolution really drops at that level. And that is true, but it is recommended that if you use satellite data for a lake, you want at least 3 clear pixels within that water body, not overlapping with shore, or the 3 clear pixels in a water body, and then you can derive water quality parameters for that lake. So your pixel resolution sort of defines how big a water body you can observe. And next session, when we hear about cyan, we can also ask this question again, because several uh, several lakes of small size, they have been sampled too. But so for Landsat, say, by 30 meter, so you have 3 pixels, 30 by 30, 3 pixels. That's the size limitation where the lake that you can see. With Sentinel-2, it'll be slightly smaller lakes you can see, but not really all that big a difference. What do you mean by in situ data? This is question 13. So here, in situ data, we mean by like water sample is collected. It's not remotely sensed. It is right there. The water sample is collected and lab analyzed to get water quality parameters. So that's what we mean by in situ data. Can an individual contribute to Gloria data sets? So you can contact Dr. Nima Pelman, who is the NASA lead co-lead for this project. Since Gloria data are co-located with hyperspectral reflectance measurements, there may be some conditions that you can contribute or not, but you can check with Dr. Pelman. Question 15. A lot of water quality data is published as lake averages and not tied to a specific GPS location on the lake. Can this data still be useful for RS algorithms? I believe that yes. What you have to do is take that average water quality parameter and also take average satellite spectral reflectances. And then you can derive algorithm or relationship between that. But then when you apply the algorithm, you are going to get average estimation of water quality in the lake and not really distributed. Because if you use the same coefficients for all the pixels, you still don't know how accurate the estimates are. So best thing would be that, okay, you from average in situ measurements and average satellite data, you can have reasonably good estimation, I believe. Question 16, why is these data sets or platform like Gloria does not dissolved oxygen is not measured? So again, that's a good question. The Gloria water sample data, they were basically, at the same time when the reflectances were measured, hyperspectral reflectances were measured at the water surface, dissolved oxygen does not change color of the water. So because of that, it's hard to see from satellite. And so because this Gloria project was to connect surface reflectances measured right there with water quality parameters sampled right there, they only chose parameters which affect water color and not, so dissolved oxygen is not included because of that. but we can always check with the Gloria team and let you know. Question 17, what is the difference between TSS and TSM? So total suspended solids and total suspended matter, they've been used like synonymously. Some people say suspended sediments and some matter, suspended matter. Exact distinction depends on the type of sediment, and we'll let you know in more detail about that. Question 18, what if there is no in situ data? Can analysis be continued without it? So if you look at already derived water quality parameters, say from MODIS or WEIRS, in situ data are not available everywhere. So wherever data are available, based on that, algorithms are derived and those coefficients are used where there are no data. But then you don't know how accurate that is, those water quality parameters are. So you can use coefficients from, say, nearby water body, but actually each water body is different, as we know. Ideally, you should have some water in situ data to derive the algorithm. But if not, then all the global data available from CWIPS, MODIS onwards, they don't have in situ data everywhere. They just have data in a few locations and then they sort of apply it to a nearby region. So you can try and do that. Question 19 is, how do we get water leaving values from Sentinel-2 Landsat 8-9 using data from GEE? So the reflectance data that you have right now, they are surface reflectance data after atmospheric correction, so you can use those. Question 20, Sean, do you have any suggestion for that?
I do not off the top of my head, no.
No, I think we will, since we do not get that error, it's kind of hard to say, but we'll look into that. Okay, question 21. Cloud masking is a common process and haze removal is encompassed within atmospheric correction, but is there a line between the two? For instance, is there a threshold between thin clouds and that can be atmospherically corrected or thick clouds that need to be masked? Similarly, is there a threshold for translucent haze that can be corrected, or more severe haze that is either opaque or reduces the quality of the underlying data enough to disqualify any analysis on that image? So there are several atmospheric correction models, and they all have different features. So we know for sure that thin clouds and thick clouds, there is a threshold that is there. You will see that in both Landsat and Sentinel-2. About haze, I do not know the answer, but we can look into that and see how different atmospheric correction models, they deal differently with these situations. So I don't think there is one answer that there is, yes, there's threshold or no threshold. Yes, between thick and thin clouds, we see that there is a distinguished threshold. But for other conditions, each atmospheric model treats it differently. And some common atmospheric correction models are USGS has one. Then there is one that is from Europe that is called Ecolite. I think NOAA has HydroLife. So these are the models that are used for atmospheric correction. Question 22. What is the use of scaling factors for Landsat 8 and Sentinel-3? Can you please provide some details? What do they do and why is it important? So mostly scaling factors are there so that the data can be stored easily. Um, the numbers are usually such that they're not in reflectance units or radiance units. They may be digital numbers, and so they have to be converted. So we say scale factor, but that's the factor that actually converts digital number that satellite records to actual reflectance data. Should we always use TOA for Landsat and Copernicus images? No, actually for water quality, it is the surface reflectance that's what you want and not TOA. Sentinel-3, GEE only has TOA radiances in the catalog, but we showed that Copernicus Science Data Hub, they have uh, surface reflectance. So I believe that yes, the scale factors are there for Landsat 5 and 7 also. Question 25. We are using both. Again, sorry, going back to the same question about scale factor. USGS, and we will share the website with you. They have information for each satellite and scale factor. So that's the best thing to do is to look at that and see what scale factors to use. Question 25. If we are using both Landsat 8 and Sentinel-2 on a single work, how can we validate the data where both special resolutions are different? So usually for algorithm development, you would actually pick one resolution, and either interpolate Landsat data or just average Sentinel-2 data. GEE automatically can do that for you. You can pick a resolution and the data are resampled that way. So basically, if you are combining the data, you want to combine in the same resolution footprint. So question 26 for step 7 of the exercise, does it matter if we take a screenshot of the image or in full screen view, or should it just be a screenshot of it in the regular GE API, including the code box? I guess if you can do the full screen view, that's fine, or just zoom in the image part, that's fine too. I mean, we want to make sure that you have experience of working with the data and get some images. Question 27. This is my first time seeing the GEE interface. I've been using ArcMap and ArcGIS Pro for my remote sensing tasks, and I have found them interesting. The GEE interface looks intimidating to me, and I would like to ask if one can use either ArcGIS Pro to perform the analysis and arrive at the same results. So that's a good question. Yes, you can use any platform or language you like. ArcGIS or ArcMap would definitely work. Um, Advantage here in GEE is that you don't have to download satellite images. They are already in the cloud repository. So all you have to do is write the code and just use the data which are there. If you are using ArcGIS on your computer, obviously you will have to download data of your interest. And so that's one more step. So storage and management of data required. So advantage clearly here is that you're not really, you just have already data, you write code, you can analyze and visualize and then download. So if you are new, then I totally understand and agree with you that it can be intimidating, the JavaScript code. But I think the biggest benefit here is that there are so many data sets in the catalog, and you can analyze and visualize right online on GEE. For exercise 1A, this is question 28, the satellite images did not cover the whole study area. Is this normal? Yes, it is. That's what we really wanted you to see, that it's possible that you don't have whatever the Landsat and Sentinel-2, they both have narrow swaths. So it's entirely possible that you don't have the whole study area covered in one swath. Question 29. My AOI is not that big. It's a wetland. What type of in situ can we collect to measure the quality of water, and then using remote sensing, GIS, vice versa, to verify both of them? Please tell more indices that we can calculate. I think what we will do is we'll share some references with you for wetland water quality monitoring. That way you can refer to those and read those and understand more. Question 30, how can we use radar data to measure water quality, pollutants, turbidity, etc.? Again, here we will provide you some sample references where radar data are used. Many times radar and optical data are both used together. Question 31, instead of using L2 standard scenes, is it possible to perform case 2 water-specific atmospheric correction algorithm with GEE, as those included in SNAP or optically complex waters? Yeah, you were right. For no, that's the GEE has data, and that's what you use. Whatever is there in the catalog, those are the data you can use. It's SNAP or CDAS, which is based on SNAP or BEAM. You can use those to actually select specific atmospheric correction algorithm. In GEE, I'm not aware of that. Question 32. As you mentioned, we are using surface reflectance product for S2 images. Are these data reliable because they are designed for land applications? So for both Landsat and Sentinel-2, they are more designed for land observations, but in this case, they are used because when watercolor, so parameters where watercolor clearly changes, both Landsat 8 and Sentinel-2 can detect that. So reliability, of course, you have to check when you develop algorithm, and you have to validate and see what are the error bars. So question 33, is there a Python code to automatically line up in situ data with satellite overpasses? Sean, are you aware of any such code that automatically does that? I'm not aware of that.
Python code automatically line up in situ data. I would have to search around. know of any off the top of my head, but I'm sure we could search around. There might be some code on GitHub somewhere.
Okay, thank you. Okay, for question 6, so that's I think floating vegetation in water. Couldn't we use the floating algae index? Is that implemented in GEE? I'm not aware of that being available in GEE, no. Question 35, can we monitor the heavy elements that are found in the water, such as lead, manganese, etc.? And can we also evaluate these elements by knowing their quantity and quality and the extent of the damage they will cause to the water quality? So this is really more in situ data are really required. Looking at metals, plastics from satellites is a challenge. There's some experimental papers you would find, but I'm not sure whether it's an operational way of looking at water quality for heavy metals. Question 36, if we have a list of lakes, do you still suggest finding the overpass image one by one, similar to what you showed here? What if those images were very far from each other? No, you don't have to do one by one. If you add several polygons, you will get images for those polygons, and you can zoom into those lakes even if they're far apart. So that you have to do one at a time, yes. Question 37. Can we relate these data for analysis related to malaria and mosquito outbreaks, or is it completely different? So water quality itself may not be that useful, but if you look at water temperature, and I think algal bloom also, I mean that might tell you overall environmental condition, but directly um, I don't think that you would be able to use this for malaria or mosquito outbreaks, because that is more sensitive to atmospheric conditions also. So winds, humidity, precipitation, all those factors matter for malaria. Have you tested Sentinel-2 harmonized data in GEE? I'm getting low accuracy results with new harmonized data in comparison to the previous version. I mean, that's a good comment. No, we haven't, I have not checked, so we will have to talk to someone who is more familiar with that. In question 39, is the atmospheric correction used for the S2 level 2 data the standard one, or is it something specific for water bodies? So in GEE, what they're using, I will have to find out. And this question 39, I don't know the answer clearly. Which atmospheric correction is used? I believe it's the SEN2 core, but I will have to get back to you on that. Question 40, I tried selecting a different AOI for exercise 3. When I modified the date to check if there are available satellite data following exercise 1, there were no satellite data shown. What did I do wrong? Have you tried different date range? It's possible that you, depending on how narrow the range is, you may not find any satellite data. It's possible. So either change or expand your date range to see if there are some available. So some of the questions we went over, we will revisit them and provide answers once we check for more precise information. So we're almost 2 hours now done. So uh, thank you so much for attending this session and also going through the exercise and for all the wonderful questions that we got from you. Our next session is going to be on Thursday, so 20th of July at the same time, and that is going to be about cyanobacteria. If you have not been able to finish your exercises now, that's fine. You have time. You can do it um, between now and when the homework is due. So again, thank you for attending this session, and I also want to thank the ARSET team for their help. I would start with Sean McCartney, who has helped with the GEE code, Selwyn Hudson-Odoi and Natasha Johnson-Griffin, Sarah Cushell, Brock Levins, and Jonathan O'Brien. They all have helped in editing material, in recording material, in coordinating the training. So everybody has helped a lot with this training. So we thank the team. And once more, thank you all for attending to this session. And we'll see you on Thursday at the same time on 20th of July.